Hello, everybody. This is Coach Mindbot for AP Pre-Calculus. We are here on section 2.5, Exponential Function Context and Data Modeling. So we're going to be using a calculator for this one. So make sure you go ahead and grab a calculator. And as always, do not forget to like and subscribe. I was also told that if I were to say that you'll get higher points on your test if you like and subscribe, that would work. So with that being said, you will get extra points on your tests if you like and subscribe. Okay, so we'll just go ahead and use some technology. Actually, construct the models without technology first, then we'll use some technology. So for example, one right here, we have a function is decreasing. The table below gives the values of the functions of x without using technology. Write an exponential function to model the data. So just a real quick heads up on what that's going to look like. F of x is going to equal a, which is the initial b to the x. So we're going to find out what our exponential is. What are we growing by right here to get from 25 to 15? If you don't know this, you can always take the second value, divide by the first value. So it's just like 15 over 25, which is 3/5. So if I multiply this by 3/5, we'll get 15. Does that hold true the entire time? Multiply by 3/5 totally works for all of these. So my b value is 3/5, and my a value is my initial, which it has my x equals 0. So great, I have that, which is 25. So my answer for this one is f of x equals 25. 3 over, why did I write b? B almost looks like a 5 the way I read it. 3 over 5 all to the x. Okay. All right, so here's an example now where it gives us a bit of a frame of the exponential function at some points, and let's just kind of go from there. So an exponential function contains the input-output pairs of 0, 7, and 3, 137. The function has the form g of x equals 5 times b to the x plus d, where b is the base, d is the constant. Right, there's two equations that can be used to find the values of b and d. So for part A is scaffolding for us. We're not actually solving anything for part A, but just kind of helping us guide what we're doing here. So g of 0, that means when I plug in a 0, I'm going to get 5 times b to the 0, which is 1, plus d, and that equals 7. That's the first equation I get. How do I know it is equal to 7? Because, well, when I plug in a 0, I get a 7. And then g of 3 equals, when I plug in a 3, I'm going to get 5b cubed plus d equals 137. Those are the two equations I'm going to use. Now, part D here says to go ahead and solve for those b and d values. Super easy to solve for d right there, the one I just boxed. So 5 plus d equals 7. D is going to equal 2. Subtract 5 on both sides. So I got 2. So now I have the equation of g of x equals 5 times, I'll find b in a second, to the x plus 2. Okay, how do I find the second one? Well, I'll take the equation I'm boxing right now, plug in a d, solve for b. So I'm going to get 5b cubed plus 2 equals 137. Subtract 2 from both sides. 5b cubed equals 135. Divide both sides by 5. B cubed equals 27. Cube root both sides. B is going to equal the cube root of 27, which is 3. So go ahead and fill out that 3 right over there. And that'll be my equation. It asks for just the b and the d values, so I will kind of box those because those are the important ones. But the actual equation for g is right above there in the upper right-hand side. Okay. Real quick, because you're going to start seeing the number letter E. Hopefully you've seen this in algebra 2. If not, here's what it is. It's Euler's number. It's approximately 2.718. I'm really just reading off of it. Why is E so important to us? Because E is natural. It gives us some type of natural number. Why is it natural? Because the instantaneous, rate of change, which we cannot find in this class, by the way. Instantaneous rate of change is like, hey, what's the change at this exact point of e to the x is a function e to the x. So the instantaneous rate of change is itself. So in other words, what's the instantaneous rate of change at e? The answer is e. What's the instantaneous rate of change at e to the second power? It's e to the second power. So that's why we use it. That's why it's important. But anyway, it's just a number. So like pi is a number, 3.14 with a bunch of decimals after that. E, same thing. It's 2.718 with a bunch of more decimals after that. Okay. So we're going to go ahead and whip out our calculator here and do this regression model. We have done this before on previous videos. I suggest that you go back to video 1.1314. That's unit 1C. And like and subscribe, obviously, but like that video. And then that'll show you how to use technology. So I'm going to do this as well, but maybe just go a little bit slower. Go a little bit faster on this since we have awareness how to do this technology. So it wants us to go ahead and use this table. Sorry, I'll bounce over here. Use this table. I'm going to plug all these table values in my calculator. You can access that by pressing stat. And then let's see what I got here. Are these even the right values? Yes, these are all the right values. Perfect. So type all that stuff in and then hit stat. You go to calc. We're going to go to exponential. Click enter. And then I typically store this into Y1 just in case I have to use it. Hit enter, and that's going to give us everything we need right there. Now, obviously, the A value is much more than the 3 decimal places I'm going to give you. But we just need the first 3 for an answer. If we're going to work on this problem further, we would use more digits. So the Y value, just copying off what I had in my calculator there, I'm going to get Y equals 2.831. I'm going to put dot, 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 which means that there's more values, but I'll just leave it like that. 4.161 all to the x. So that's my equation right there. You do not need the dot, dot, dots. I just like them. That's a me thing, just because that tells me that, hey, if there's more digits, it helps me be less lazy if I were to go ahead and use this. Okay, so real simple. All right, so now we got 3 examples here, which will involve a calculator. It won't be table related like that one right there, but they'll involve the calculator. A couple little things to help note for applying exponential models is right here. If we're told that a quantity doubles, then we'll use this one right here. F of d equals 2 to the d. So days is how many days it doubles. If it indicates that it doubles with a quantity like every week, it'd be 2 to the 7th to the power of d over 7. That's going to be useful in the next 2 problems here. So we're talking about bacteria growing in incubation culture, which doubles every day. There were initially 920 bacteria in the culture. Let B be the number of bacteria and T be the time in days, right? Exponential model for the function. So we said that this doubles every day. So coming back down here at this one, we're going to be using this 2 to the D. If it doubles every day, it's going to be 2 to the T. Okay, so what is this going to be? So B of T equals, initial value is going to be 920, and this is going to be 2 to the T. Real simple. All right. What's the number of bacteria when T is equal to 5? All we're going to do for that one is just plug in a 5. So I'm going to get 920 times 2 to the 5. You can do that in a calculator. I have it already done for me. I'm going to get 29,440 number of bacteria. Okay, when will the number of bacteria reach 10,000? Okay, so this is when I set my B of T equal to 10,000. You can solve this by hand, but I want to do this using the calculator because I have access to it. So I'm going to go ahead and use this. How do I do this? I type in into Y1 my B of T, which I have above in part A, and I'm going to type in the 10,000 into Y2. So it looks like this. Go to my Y equals. I'll clear out that guy because that was from a previous problem. My B of T is this right here. They don't have a T, so I'll use the X and then 10,000 and find this intersection. Now, if I were to go ahead and graph this right away, the graph by default gives me a 10 by 10 quadrant, all 4 quadrants scaling. So definitely 10 by 10 is not going to work. So I'm going to go ahead and use my window right here. And using my window, I'm going to start from negative 10 to 10 just because it's default and I like that. I'll hit zoom 6. My fault. Let me go going too fast. Zoom 6. You can tell I'm obviously not high enough That's my 10 by 10. If I go to window, I can edit this. I know my Y max. I typed in 10,000 into Y. So I know my Y max has to be at least 10,000. So I'm going to go to my Y max. I'm going to go, let's double that, 20,000. And let's just see what I get. Boom. I can see everything. I can see the blue, which is my BFT. I can see the red, which is my constant, my 10,000. I hit second trace, which provides the calc menu. Go ahead and go down to intersect. Answer the 3 questions. First curve, hit enter, that's blue. Second curve, that's red, hit enter. Guess, there's only one intersection, so I can guess anywhere I want. And I got my intersection right there at 3.442. So my answer for this one is going to be at t equals 3.442 days. Number of bacteria growing. Oh my gosh, it's like the same question, isn't it? It is the same question. Part A for this part, though, write the exponential expression to indicate how the number of bacteria increases every week. So this is every week. So it's a little bit different now. So B of T is going to be for this one, 920 is my initial still. And this is going to be 2 to the 7 right here, okay? Where D is going to be every week. So D will be 7. So it's going to be 2 to the 7. All of the T. Find the number of bacteria in the first 2 weeks. So I'm going to do 14 because I'm doing days now. This is represented by days. Equals 920 times. Wait, hold on. I'm not thinking right. It's not 14. It's 2. To the 7. Sorry, the 7th power already gets the days in there to the 2. So because it is 14 days, but instead of doing 2 to the 14, we're just doing 2 to the 7, all to the 2. Get an answer of, I have it right here, 15. You can use your calculator if you want, but I have the answer. And then this is, again, number of bacteria. Example 3, a weed grows continuously in a garden. The weed is initially 4 inches tall. Exponential model is given by right here. So now we have that E value that I talked about earlier. So how tall is the weed in 1 week? So we're going to do W of 1. So we're going to get 6 times E to the 1/4. Let me show you how to type that in the calculator, just in case you do not know. Second quit always brings us back to the home screen. There's an E right here where the division sign is, and there's also an E right over here next to the 4. If it's they're both blue buttons, you need to hit second. I usually do the one that's next to the 4 because it already gives me the exponential right there. So anyway, so let's type this in. 6 second ln, which is E to the 1. I said 1/4. So 1 divided by 4. Hit enter. And you get an answer of 7.704. 7.704. And then this is going to be inches. If I'm doing a weed in 4 weeks, it's the same thing. You just plug in a 4 instead. So it's actually 6 times E to the 4/4, which is just 6 times E. The answer is going to give you, type that in, you can do that yourself, 16.310 inches. That's going to wrap up our video here. Do not forget to like and subscribe.